Dear students, today we discuss about the expression for the magnetic induction at a point due to straight conductor carrying current. You know what is conductor? Conductor is a type of solid material which conducts heat and electricity. So it easily conducts the electricity. So suppose we pass a current through a wire, a straight wire or straight conductor, a magnetic field, a magnetic induction is produced around this. Our aim is to derive the expression for the magnetic induction at a point due to a straight. The point may be nearer to the wire or far away from the wire. So what is the magnetic induction at this point? If the distance varies, what happened to the magnetic induction value? So we are going to discuss in this circuit, in this class. Consider a straight conductor. It is a straight conductor of carrying current I. Yeah, current I is passed through this conductor. This represented by X and Y. It is the part of the wire. The current I is passing through this conductor in this direction. So the current I is passing through the conductor XY. Now we are going to select a point from here. We can select anywhere in this area. So suppose we are selecting the point P here, a perpendicular distance from the conductor. It is the perpendicular distance from the conductor. In this wire, we are considering a small element AB. It is the small portion AB. Suppose we are considering the small element AB of length DL. Let BP, this area, this is represented by the distance R, and the angle between OBP, here OBP, here from O, B and P, this angle. This is taken as theta. OBP is equal to theta. We know that the magnetic induction at the point P due to this element dl is given by the change in magnetic induction. dB is directly proportional to current passing through it and the length of the element dl and the angle sin theta and the distance from the square of the distance from the conductor to this point P. It is R square. Already we have derived this formula in the last class. From point P, draw a perpendicular line BC to PA. BC to PA. See here. This line. It is the perpendicular line drawn BC to this PA. It is BC PA. So let the angle OBP this angle is taken as phi, and the angle BPA is taken as d phi. It is taken as d phi. Then BC is equal to this length. This BC is equal to dl into sin theta. These angles are both, here it is taken as theta. So dl sin theta. So dl sin theta is nothing but r into d phi. This angle is equal to this angle r d phi, r into d phi. So dl sin theta is equal to r into d phi. On substituting this value, dB is equal to mu naught I dl sin theta by 4 pi r square. We know dl sin theta is r d phi. So mu naught I r d phi by 4 pi r square. On simplifying this equation, we get mu naught by 4 pi r I into d phi. From the diagram, the angle OPB is taken as cos phi. This angle is taken as cos phi. It is OP divided by PB, this side and this side. So OP by PB is equal to A by R. We know OP is the length A and PB is R. So R is equal to A by cos phi. Substitute the value of R in equation 3 here. On substituting, we get dB is equal to mu naught 4 by I d phi. The value of this is I d phi by A. On simplifying, we get dB is equal to mu naught by 4 by I cos phi into d phi by A. The direction of dB will be the perpendicular to the plane containing dl and r. So it will be directed into the page at the point P as shown by the right hand rule. When the current is passing through the conductor, the current direction is taken as a thumb direction, and the other fingers indicates the production of magnetic field. It is the right hand rule. So when the current I is passing through the conductor, a magnetic field is produced here. So it is the right hand rule. When the current I is passing through this direction, the magnetic field is produced like this. So it indicates the current. This other fingers indicates the direction of magnetic field produced in the conductor carrying the current I. Let phi 1 and phi 2 be the angle made by the two ends of wire at point P. So it is the two ends. Here it is phi 1. Here this angle is phi 2. So the magnetic induction at the point P due to the whole conductor xy is, on integrating this from the lower limit minus phi 1 and plus phi 2. So B equal to mu naught I by 4 by it is a constant term. Integrating the cos phi term, on integrating we get sin phi into phi 1. The lower limit phi 1 minus phi 1 and upper limit phi 2. On substituting, sin phi 2 minus sin of minus sin minus phi 1. So we get positive sign here. So we get mu naught I4 by a sin phi 2 plus sin phi 1. Sin phi 2, if sin phi 2 takes the 90 degree, we will have sin 90 is equal to 1. So we get the value 2. B is equal to mu naught I by 2 pi A. So the magnetic induction B depends upon the current passing through the conductor and the reciprocal of the distance from the conductor. So it is the final equation.